All right. Any questions before we get back to trees? All right, well, we were talking about making a tree class. And we were going to have a separate class for the nodes. So let's write some code. So here's a single node. So let's do a tree of strings, just for fun. So we'll have a data piece, which is a type string, and we'll have left and right pieces, which point to subtrees, and those will be T nodes. And let's make a constructor that will build an initial node containing a given string, and its children will be null. Public. So we talked about, I believe, this idea that our tree class is going to have an add method, but our T-node class is also going to have an add method. Did we talk about that? Okay. So this is basically going to be a wrapper around that. So let's write the add method for a node, right? That's going to be the usual recursive call itself kind of add method. And so our tree cannot be null because we're inside, right? We're asking to add to the tree whose node we're inside right now. In other words, this is the root of the tree. So we can't have a case where the root is null, otherwise we wouldn't be inside this method at all. So we know that we have a root, and we simply need to know, should we add to the left or the right? So for me, compare to always confuses me. So if A dot compare to B is going to be positive or negative, we'll take a vote. I think this is going to be negative.
So this is less than the documentation.
Yeah, so I could read the documentation, but I know that if I get this wrong, our list is just going to come out backwards, and we'll switch this up. So I'm going to be lazy. I'm just going to believe that this is correct. So if data dot compared to S is less than 0, we'll insert on the left. And so normally we could just say go to the left node and add your string. Anybody not sign in? All right. Backing around after. So normally we would just say, okay, we want to insert on the left, let's take the left node and call its add method. The one possible complication here is if there is no left child, then left will be null, and this will throw a null exception. So, got to see if the left child exists. So if the left child is null, make a new T node containing the string S and set left equal to that. Child. Alright, so if left is null, make a new node, set left equal to that. Otherwise, left exists, so call its add method to insert our node. And then we're done. Otherwise, we want to insert on the right. Alright, so exactly the same drill on the right. If right's null, set right equal to a new node, otherwise call the right's add method. And that's the whole add routine. So does that make sense? Alright, so for the tree we need a root, which is going to be a T node. So we initialize the root to null, that makes the tree empty. And let's make an add method that's a wrapper around the node's add method. So public void add string S. So if the tree is empty, how do we add a node? We just create a node and we call that the root. Going from an empty tree to a tree with a single node is easy, just make the root that single node. Alright, so if root's null, set root equal to a new T node and return, and you're done. Otherwise, the root of the tree exists. So how do we add to the tree?
Compare and call.
Easier. That would work. But even easier.
Root.add.
Root.add. Couldn't be easier. Root node exists and nodes have add methods. So root.add says in the tree whose root is root, add this node S.
Is the return necessary?
Nope. I just kind of put it in because I had it up in the root null case and I feel bad if I leave it off. But it's completely not necessary. Alright, well there's a decent tree class. Alright, so we'll push 5 things into our tree. And we're not going to do anything with this. But it compiles and it runs and it doesn't blow up, so that's promising. So let's talk about traversal. And rather than make a traverse method that prints out the nodes, let's just make a 2-string method. And then in our main program we can choose to use that if we like. So I'd like that to print out a space-separated list of these words. Maybe put the words in angle brackets or something. So we want a 2-string method in our tree class. And again, we can't really do recursion on the tree class itself because the thing we're going to recurse into is usually the root, or the root's left or right child. Those are t-nodes. And so if we write a method in the tree class, it can call a method in the t-node class, but the t-node class can have things that call methods in the t-node class. So we're still going to have a wrapper inside tree, which basically the 2-string is just going to call 2-string inside the t-node. So if we want to print a tree, here's some pseudocode. Right, what do? We print the left subtree recursively. Let's call this myPrint. So we call myPrint on the left subtree, and then we print out the root node's data, and then we recursively call myPrint on the right subtree. And you have to make sure that these aren't null. Maybe somewhere. So that's the basic plan. So how do we do this with 2-string? This is inside t-node. So put on your recursion sunglasses, right? Everything you see through the lens of recursion. To print a t-node, to print the tree rooted at t-node, right, rooted at ourselves, we want to print out the tree rooted on the left subchild, and then we want to print out our data, and then we want to print out the tree rooted on the right. Okay, but we don't want to print, we want to add these to a string. So let's make an empty string to save our result. And we only want to do this if the left tree is not null. So if left is not null. So how do we take the string corresponding to the left subtree and append that to this string called result? We want to take the string corresponding to the left subtree and append it to result. And we still got recursion sunglasses on.
Pass result to the left.
Say again?
Pass result to the left.
Pass it how?
Result plus 2-string dot left.
So result equals result plus toString dot left, but you know, if we just do left, since left has a toString method, that will take the string corresponding to that tree and concatenate it to result. And then we can concatenate the data, and then we can say if right is not null, result equals result plus right. And that should work. Alright, so result's going to be our return string. Is there anything on the left to append? And if so, that should call left's toString method, which should give us a space-separated list of the words in the left subtree, and that'll get appended to result. And I'm going to have a trailing space at the end of toString, and I'm going to actually depend on that, because here it's going to leave a space after the last word, which is a good thing. So then we need to put on the root node's data. So we'll tack on the data, followed by a space. And then the same thing on the right. So there's our toString method. And it's basically 3 lines. Left is not null, append the left, append the data. If right's not null, append the right. So what does tree's toString look like? We've got a toString for the node class. What is toString? Yeah, basically just call roots toString and return that. With the usual caveat that if the root is null, we'll just return an empty string. Otherwise, I could call root.toString, or I can just concatenate root to a string, and that'll force it to use root's toString. toString for the tree is even simpler.
So if you don't add the empty strings, the root won't be called toString?
I think it will give me a compile error.
Because root is not a string.
Because it'll say it doesn't know how to convert that, but let's see. So yeah, incompatible types, tnode cannot be converted to string.
Okay.
And I misspelled insert. So main, we're still using t, right? We're saying print t equals t. Let me make this uppercase just so we don't get confused. All right, ready to try it? Hey, we got the compare backwards. I got the compare backwards. So why is that backwards? If data compared to
The result is positive?
yeah, so I'm going to actually force myself to read the documentation. The result is a positive integer if this string follows the argument. So if this string comes after the argument, it's positive. So if this string, this is saying this string comes before the argument. Feels like it should be less than.
But aren't we traversing left to right though? So shouldn't it be printing out left to right? So
Should be printing out left to right, so smallest to largest.
But aren't you storing your
Your comparison is backwards of what you would think it is. You're comparing data to S, and then you're adding it. You're creating a new node with S.
Right, so I'm comparing data to S. The result is negative if this string precedes the argument string.
So you're comparing it, then you put the string that's bigger on the left-hand side of the string that you're currently on, right? So you're creating a new node on the left. The
Yeah.
argument string.
Right, okay, I really wanted s dot compare to data. Or I could just do bigger than 0. So the node that we're inserting comes before our current node, right? Okay. Okay, so I could have just made it bigger than 0, but all right. Does that make sense to everybody? Like I say, these, for me, they always are confusing, but it's easy to tell if it's backwards. All right, so there's our sorted data.
So how can it compare this ladder?
Say what?
How can it compare this ladder to the tree the left around?
So if the thing you're inserting comes before the root, you want to insert it to the left of the root. So here's dog. If you get a new word cat, right? Cat dot compare to dog, is going to be less than 0, right? Which tells you that this comes before dog, so you put it on the left of dog. So really easy to use, right? Construct a tree, add things to the tree, turn the tree into a string and print it out. And we don't care about what's going on inside all of these things. And the fact that t.add is really just a wrapper to t.root.add, right, is hidden from us. So questions about this? So this is just an example, okay, of the tree implementation. And it's topical because you're going to be playing with trees in PA4. And you're going to be playing with a particular type of tree called a decision tree. And I think we might have touched on this at the end of 222. Does that sound familiar? So let's talk about decision trees. So PA4 is going to be your own implementation of this 20 questions game. So 20 questions, somebody thinks of something and then somebody else tries to guess what they're thinking of by asking yes/no questions. And in the actual game you're allowed like 20 questions. We don't have to limit it in this case. So you think of something and the computer is going to try to guess what you're thinking of. Okay, so it's going to ask you yes/no questions. You're going to answer those honestly, and it's going to try to figure out what you're thinking of. That's the overall behavior of PA4. All right, so who wants to think of something? All right. You are thinking of a dog. Am I correct? No. Okay. So what were you thinking of? A computer. Okay. So you were thinking of a computer. I thought you were thinking of a dog. Okay. Tell me a question where the answer would be yes for a computer and no for a dog.
Is it living?
Is it living? Is it not living? Okay, so is it not living? And if the answer is yes, it's a computer. If it's no, it's a dog. Okay, thank you. Who else wants to think of something? All right, you got something in mind? All right, I'm going to guess what it is by asking you questions. So is it not living? Is it dead? Yes, it's not living. I know what you're thinking of. You're thinking of a computer. Am I right? No. Okay. So what were you thinking of?
Mummy.
A mummy. Cool. All right. So here's what we're going to do. We're going to make a new tree with mummy on one side and computer on another. And can you tell me a question where the answer is yes for a mummy and no for a computer?
It used to be alive?
Okay. Did it used to be alive? And where I used to have computer, I'm replacing that with a new tree which has a question, and the yes answer is mummy and the no answer is computer. All right, thank you. So one more time, who wants to think of something? All right. Is it not living?
No.
No. Okay, you're obviously thinking of a dog.
No.
No. Okay, what are you thinking of?
A butterfly.
A butterfly. All right, so we say butterfly and dog. And is there a question that differentiates those?
Can it fly?
Can it fly? Hey, I know some fun dogs. And so we replace dog with that question, can it fly? Yes is butterfly, no is dog. Yeah, in a plane. All right, so we're building a decision tree. Okay, the next time that we play, if somebody thinks of a mummy, a computer, a butterfly, or a dog, we're going to be able to guess the answer correctly. And we do this by simply starting at the root, and the root, all the nodes in this tree are questions until we get to a leaf node. The leaf nodes are answers. And each node has two children. The one on the left corresponds to a yes answer, the one on the right is a no answer. So to play this game, I take this tree, and I start at the first node, and if it has children, if it's not a leaf, I ask this question. I get a yes or no response. I follow it down to another node based on their response. If that's not a leaf, I ask that question, follow it down based on their response. This is a leaf, I say, okay, here's my answer. And if you were thinking of a butterfly, great. If not, then I'm going to create a new tree with the correct answer on the left, butterfly on the right, and a node that differentiates those as a question, and that's going to replace this leaf. So the more you play this game, the better it gets. And once somebody has guessed something once, right, forever after, the computer should be able to guess if that's what somebody's thinking of.
Can it balance itself?
No, it actually gets pretty horribly unbalanced. And I'm not sure what the mechanics are of trying to make it more balanced. But let's look at this question of number of nodes and depth. So we have a depth of 2 or 1, depending on how you start counting. Basically 2 questions that we're going to ask. And in this case, we're able to differentiate 4 different things. Right, now this is a nice full tree. But if it stayed full, if we added 1 more question for each of these, how many things would we be able to differentiate? 8, right? Because this would take us to 2 answers, 2 answers, 2 answers, 2 answers. And so if you're actually playing 20 questions, how many different things can you differentiate theoretically? 2 to the 20th. How big is that? Yeah, that's 1,000,000.
1,048,576.
Cool. So over 1,000,000 different things that you can differentiate by asking 20 questions, which is pretty cool. So that's the basic data structure we're going to be using in PA4. It's just a plain old binary tree, but it's not a binary search tree. Okay, there's no alphabetizing or sorting going on here. There's no notion that, mummy comes before a computer or something like that. The organization of the tree is we think of these as questions, and if the answer is yes, it should take us to the left. If the answer is no, it should take us to the right. And so everything over here on the left should correspond to a yes answer of this question. So maybe that's the overarching principle of a decision tree. If you look at any node, that node is a question, right? Everything to the left of that node answers yes to that question. Everything to the right answers no for that question. So we're splitting the set of possibilities, roughly in half based on each question. So PA4 is going to do a few things. First of all, it's going to play this game. It's going to ask the user to think of something, and then it's going to start asking questions and taking in answers of yes or no. And when it gets to a leaf node, it's going to announce what it thinks you're thinking of. And if that's correct, then it can gloat and call you a silly human or whatever, right? But if it's not correct, then it's going to ask for some help in improving itself. So it's going to ask what you were thinking of, ask for a question to differentiate what you were thinking of from what it guessed, and then it's going to update this tree. The other thing it's going to do is it's going to save this information on your hard drive. And every time that you run your program, first thing it's going to do is read this information from your hard drive, so it starts with the same tree that it left off with. So that as you play this over time, right, it should get better and better. And so we have to think about how to write this out to a drive and how to read it back in. And we'll dig into the details of that on Friday, because there's some very specific ways you can do this that will be pretty straightforward, and there's lots of other ways you can try to do it that'll be really confusing and may not work. And you can choose whichever one you want. But basically, we're going to traverse this in a particular order to write it out, and then to read it back in, we're going to have a really short recursive algorithm. But if you look at this file, it's not going to make any sense. If you just kind of look at it, you're not necessarily going to see this right next to this or that, right? So, and then the other thing is, and I gotta find it somewhere. All right, let me hop on the server. I'll have to find it. Anyway, we have access to a database with lots of decision tree information inside it. And heck, I'm going to find it anyway. All right, so anyway, that's the setup. And we have a database that has, I don't know how many different things inside it, but it's a huge decision tree stored in a flat file. And so once your program is able to save this format and then read it back in, you can read in that as your starting file and play 20 questions and think of pretty much anything reasonable. I think it's built around creatures, so you have to think of some kind of living thing. And it will do a decent job figuring out what you're thinking of.
So how can we get the answer? Sometimes have no answer there.
What do you mean, no answer? Like if it's not the right answer?
Yeah.
So you're thinking of a cat, right? So is it not living? No. Can it fly? No. It must be a dog? No. Okay, so then it says, tell me what you were thinking of. I was thinking of a cat. So you make a new tree with a cat on one side, the thing you guessed on the other. Tell me what the difference is. You know, a question that says yes for a cat and no for a dog. So does it meow? And then we replace this node with that question. Okay, the next time you play, if someone's thinking of a cat, is it not living? No. Can it fly? No. Does it meow? Yes. You're going to guess it's a cat. And if it's a lion, then you'll turn this into another question, right? Is it big? And so the other thing on PA4 is you get to design it however you like. Okay, this is what it's got to do under the hood. But you can do this from the command line. You can do this with a GUI. Okay, you can stylize it however you choose. GUIs are more fun to work on, I think, because you've been writing command line stuff like throughout school. So, and this is a pretty straightforward GUI, right? You need a box for the question. You can have a yes button and a no button. And you know, you can have a little counter for how many questions it's asked, and you can do all kinds of fun stuff. So if you want more practice on GUIs, it's an opportunity. So questions about decision trees or how this plays out. We're getting to the details of PA4 Friday.
So just insert no delay.
Sorry?
Just insert no delay.
Yeah, no deletion involved here. It just grows and grows and grows. And it can get corrupted, right? If somebody messes up, and doesn't answer correctly, right, it can go down and think that it's not guessed the right thing. And if you put in a good differentiating question, right, that'll probably fix it up. But certainly if you put in a bad question here, you can corrupt the database, and then forevermore, right, it'll go the wrong way. Yeah?
Will trees be on the midterm?
No. Yeah. Yes?
So to like prevent corruption, could you like run some kind of test to see if something's already in the tree, like in two places?
Yeah, except that practically speaking, when you start making this thing really big, especially if you crowdsource it, which is what this database file was, I believe, it gets into wiggle room, right? So is it large, right? Is kind of a subjective thing.
Yeah.
You know, is it friendly? And when you start throwing in like mythical creatures, it gets even crazier. So it's going to have some noise in it, and that's just kind of part of the charm of it. But yeah, if you wanted to do that, I think that would probably be a good catch to see if something already led to this. Because if you get to it through two different paths, then somewhere there's a question that you could answer yes or no and still get to a cat, right? And that's either an ambiguous question or there was a mistake. So yeah, that would be a good way to catch that. And you could get into all kinds of crazy stuff, right? So you could record the path that they take to get to their answer, and then if they create that duplicate, right, you could ask them to review the questions, and you know, you could find the question that they could have gone either way and say, think about this again.
Maybe something like illegal, like hello again, it's gonna be kicked out again.
Mm-hmm.
Do you need that?
If they're hitting yes, no buttons, right, they can't really make a mistake. If they're typing things in through a command line, right, you want to make sure they're saying yes or no. So you can require certain types of input and ask them to enter again if it doesn't look like a yes or a no. But I'm not sure there's anything that's going to cause them to be kicked out. All right, any other questions? Last 15 seconds on the exam. Okay, sign-in sheet is somewhere. If you didn't sign in, sign in. I will see you tomorrow.